Hello, thanks for joining. My name is Flavio Guzman. I am the editor of Pharmacology Corner. In this video, I am going to talk about the pharmacology of opioid receptors. In this presentation, I will discuss the following topics: a general classification of opioid receptors, their cellular actions, mu, delta, and kappa receptors physiology, anatomical distribution, as well as their selective agonists and antagonists. After that, a short review, and finally some words on the opioid receptor-like one. Here we have divided opioid receptors in two main groups: classic and non-classic. Classic receptors include mu, kappa, and delta receptors, and non-classic receptors include the opioid receptor-like one. We will continue by reviewing the chemical characteristics of opioid receptors. This figure shows a schematic representation of a typical 7-transmembrane receptor. As we will see in greater detail in the next slide, opioid receptors are G-protein coupled receptors. Each receptor consists of an extracellular amino terminus, 7 transmembrane helical twists, 3 extracellular loops, and 3 intracellular loops. Finally, a carboxy terminus. Here we have a presynaptic neuron with the 7-transmembrane receptor coupled to a G-protein. The G-protein is made up of 3 subunits, alpha, beta, and gamma. Now, inside the slide, we are focusing on what happens to calcium and potassium channels before the opioid receptor is activated by an agonist. The blue protein represents calcium channels. Calcium channels are open when the opioid receptor is inactive. This allows the entrance of calcium ions into the presynaptic neuron. Potassium channels are depicted as orange proteins. Potassium channels are closed when the opioid receptor is inactive. This prevents the exit of potassium ions from the intracellular space to the extracellular space. But what happens after the opioid receptor is activated by an agonist? The green circle represents an opioid agonist, in this example morphine. After morphine binds to the receptor, it triggers its activation. G-protein signaling is responsible now for the two main changes in the neurophysiology of the presynaptic neuron. The first change is that calcium channels are now closed. This prevents the entrance of calcium inside the neuron. And the second change is that potassium channels are now open. This allows the exit of potassium channels from the intracellular space to the extracellular space. The closing of calcium channels and the opening of potassium channels has effects on neurotransmitter release, as we will see in the next slide. A reduced influx of calcium and an increase in potassium efflux lead to membrane hyperpolarization. These electrophysiological changes produce presynaptic neuronal inhibition. This inhibition translates in a decrease of neurotransmitter release into the synaptic cleft. This includes glutamate, acetylcholine, norepinephrine, serotonin, and substance P. This is one of the mechanisms by which presynaptic opioid activation modulates neurotransmitter release.